Hi, and welcome back for this third, basically, part of this review for exam 3. Anyway, basically, I'm going to try to go a little bit faster than before because we're planning to do this anyway in class. So the point, go a little bit more in depth in class on Tuesday, next week. So anyway, uh, I'm looking in here still at these problems that we did. The next problem that we need to discuss is this. I think we did this one. I think we did also problem 5. So problem 6, basic problem 7. I know we did it in class, so we're going to skip through from when we do 6. So let's talk about 6. So 6, basically, it says in here. Let me get this tool in here. Let me get this out of the way. Let me get my pen. Anyway, so basically in 6, what you have a can of soup and it's filled. So we really don't know. We can't use the formula 1/2 of I omega, 1/2 of mr squared for the moment of inertia because we don't know the distribution of the mass in there. So it's not uniform necessarily distribution. And that formula assumes that there is a uniform distribution. So here's a problem. You have a can of soup basically that is more of a cylindrical shape, and as it's falling in here, it falls from a height, in this case 10.8 centimeters. No, the height of this one is, so this is how it looks like. So this is how the can look like. So this is the length is 10.38 centimeters, and the diameter is this whole thing, not just the radius. The diameter is 6.38 centimeters. So basically, if I'm interested in the radius, is half that much. Okay, it is placed on its side at the top of a 3-meter long incline. So this incline has a distance in here of 3 meters. So that's really the one piece of information. The other thing also is the angle in here is given to you as 25 degrees. Okay, and is then released to roll. And is then released to roll straight down. Okay, it reaches the bottom in about 1.5 seconds. So the time it takes for it to come down is 1.5 seconds. Okay, the question is, assuming mechanical conservation of energy, calculate the moment of inertia. So what I'm going to say in here, when it reaches the bottom, it's going to be spinning and its center of mass is moving. Remember, the kinetic energy in this scenario is going to be equal to 1/2 of I around the center of mass. That's what we need to know, times its omega squared plus 1/2 of the mass of this object times the velocity of the center of mass squared. This we did it in class. When it started, in here, the kinetic energy is equal to 0. When it started, though, the potential energy in this case, PE, is equal to mgh, where h is this height, okay, which is in this case clearly is equal to d times sine of 25 degrees, okay, and because d is the hypotenuse in this right angle triangle. And when we're going to put it in the bottom, because the only reason why it's mgh is because we put the potential energy when it reaches the ground to be 0. So we have the mechanical energy before must be equal to the mechanical energy after, and we should be able to find things around. So, okay, sorry, for some reason it's not moving for me down as fast as I wanted. Anyway, so you equate the kinetic energy plus 0, which gives me 1/2 of I. I'm going to drop the center of mass in here symbol because we know that all of these things are calculated with respect to the center of mass. Omega squared plus 1/2 of mv squared, and v in here is that of the center of mass because there are parts of it that are moving faster and other parts that are not moving at all. So the center of mass minus 0 is equal to the change in the potential energy in this case, which gives me the final minus initial. Remember, the initial was negative to begin with, so it's going to be at the end the energy. I'm sorry, plus the final, which is 0, minus the initial, which is mgh, equals to 0. That's the change in the whole mechanical energy. Okay, so and this one is minus 0, so everything is perfect. So this is the final, the initial kinetic energy. This is the final potential energy. This is the initial energy, and the difference is coming from formula in here, the change and the change. Anyway, so this gives me a formula for I, but I need to know what this V is in terms of what was given, okay? And this omega also, because I don't know it. I know M, I know G, and I can calculate H, okay? Which is just sine of theta times sine of 25 degrees times 3 meters. Okay, so the V's now and the omegas. First of all, it's clear that the V and the omega are related to each other through this relationship, and that's because when it was spinning coming down, it was not sliding. So the center of rotation, the instantaneous center of rotation is the bottom, and the center of mass is the distance r, and the displacement along the arc, which is the actual displacement coming down, is equal to the angular displacement theta times the radius r. And from here, we're going to take that derivative and find the relationship between omega and r, omega and v. Okay, so that's one relationship, but we still don't know v. If we know v, we can find this term, and we can find this term through this relationship. So the v. There was something that I know I did not emphasize a lot on it, but it's simple algebra. I know that you guys are capable of doing it. That's why I did not really emphasize on it. Remember when we did the kinematics, we arrived to this expression? For uniformly accelerated motion, that means an object that has moved with constant acceleration. And also we found that V is equal to V naught plus AT, or delta T in this case, change in time. So the lapse in time. Anyway, so we can use this relationship to find an interesting case in this case only when A is constant, the acceleration is constant. Okay, so it's not true all the time. Let's just take this, rewrite this equation as follows. Delta X and V minus V naught is equal to A delta T. Okay, before dividing, I have to make sure that V is not equal to V naught, and then also delta T is not equal to 0. In other words, there is a lapse of time so that delta T is not equal to 0 for this relationship to happen. And that ensures that the velocity has changed. So V is not equal to V naught. If that's the case, then I can divide V squared minus V naught squared, knowing that V naught squared minus V naught squared can be written as the product of the difference plus the sum of the two terms, because it's a perfect difference between perfect squares. So having said that, when I divide, the V minus V naught cancels the V minus V naught, and I will be left with just V plus V naught equals to, and the A cancels the A, of 2 delta x over delta t. And this gives me an interesting result in here, that the average velocity, which is this expression VAVG, is equal to the sum of the two velocities, namely the final plus the initial divided by 2. Okay, and this comes in handy because then I know what the average velocity in this case. It's the distance traveled from the top to the bottom, which is d, 3 meters, divided by the lapse of time, which is 1.5 seconds. That's how long it takes for it to drop down. And so the final velocity, which I don't know, that's of the center of mass, by the way. I dropped the center of mass just because I were just for writing less symbols and stuff. So started from rest divided by 2 must be equal to the whole distance divided by the time t, that was 1.5 seconds. From here, we can find the velocity of the center of mass, and we have d, which is 3 meters. We have t, which is 1.5 seconds. And then at the end, we also have omega now, since we have v, which is twice this number divided by that. Since we have omega, we can plug it in here and solve for I. Okay, once we have I, where is it? Assuming we can calculate, so we should be able to calculate it. Now, which pieces of data, if any, are necessary? Obviously, it's going to be that height of the. Remember, the moment of inertia is going to be equal to 1/2 of mr squared in this scenario, so the length. Why can the formula be used? We can't use it because of the fact that, again, the mass distribution is not uniform. As a matter of fact, if you calculate 1/2 times mass times this radius squared, you're going to find a different value for the moment of inertia than what is computed in here. Okay, so problem 6 done. Problem 7, we did it in class, I know that. And problem 8 in here, it says rigid body of negligible mass, rigid rod, of negligible mass, and lying in the y direction, the system rotates about the x-axis. So basically, it's spinning going around the y-axis. Okay, The moment of inertia, so find the moment of inertia of the axis, about the x-axis. So since I have 3-point particles, so we're talking about problem 8 now, okay? So the moment of inertia in this case is going to be there is no 1/2 in this case, these are point particles. So it's going to be m1 times its distance from the axis of rotation, which is in this case 3 meters, times, so let me write the numbers quickly. So it's 4 kilogram times 3 squared, because everything is in SI, plus 2 kilogram times the distance is 2 meters, so it doesn't matter if it's on below or above the axis, because you're going to take -2 and square it, so it's going to be 2 squared, or -2 squared if you wish, so the negative is going to become positive, plus the 3 kilogram times the, again, same thing, -4 squared. Okay, so you have 4 times 9 plus 2 times 8, or 2 times 4, which is 8, plus 3 times 16, okay? So that's the moment of inertia, okay? And then the tangential speed of each particle, the tangential speed of each, I'm sorry. So we found the moment of inertia, the total kinetic energy, which is 1/2 of I omega squared. Since kinetic energy, since we just assumed that we calculated I, which is straightforward, times omega squared, and omega also is given. It's in here, 2 radians per second. So omega is, so this is equal to 1/2 times omega, which is 2 squared, times I, and I refers to this calculation, okay? And then the tangential speed of each particle. So again, the velocity of the first particle is equal to its distance, which is 3 meters times omega. So it's 3 times omega. So this is for particle 1. Particle 2 is at a distance of 2 meters. So again, it's 2 times omega. Again, we're looking at the distance. We're not looking at the coordinate. It's going to be a positive number. And V3, the speed, not the velocity. Okay, V3. The question is asking for the speed. So V3 is again equal to 4. The distance is 4 times omega. Okay. So we have that, and omega is 2, by the way. So this is 6, this is 4, this is, what is it, 8 meter per second. So again, this is 6 meter per second. This is 4 meter per second, 4 meter per second, and this is equal to 2 times 4, which is 8 meter per second. Those are the speeds, okay? The kinetic energy using this formula. Now, the kinetic energy using the other formula basically is just the sum of the individual kinetic energy. So 1/2 of the mass is 4 times this speed, which is 6 squared, plus 1/2 the mass is 2 times this speed, which is 4 squared, plus 1/2 of, again, the last mass is 3 times the speed, and the speed is going to be equal to 8 squared. So that's the kinetic energy. So remember, we have computed the kinetic energy using 1/2 of I omega squared. Now we're computing it in a different fashion using 1/2 of I times 1/2 of the mass times velocity squared for each individual particle, and we should find the same answer. So the answer to E is both answers must be the same. Okay. Okay, if you find any difference, please let me know, because I will be surprised. Okay. Anyway, because honestly, the formula for both is in this case, because the airborne particles are the same. Okay, unless we made a mistake somewhere. Okay, block 9. I'm gonna drop this one. I'm going to come back to it. I know I'm running a little bit of time, so I'm going to come back to 10. 10 in this case is gives you a rigid body, and it has a 3-point particles again of all the same masses m, and it wants to find the moment of inertia around the center of rotation that is fixed at a distance 2d/3 for this one, and 1/3 of a d from this one, and d from this one. So the moment of inertia again is going to be, since they are point particles in this case, for the first mass is going to be, it's going to be 1/2 of m for each and every one of them. Okay, 1/2 of m. There is no 1/2. Okay, moment of inertia, there is no 1/2. It's mass times distance squared. So mass times this distance, which is 4d squared over 3 plus d squared, 3 squared that is, over 3 squared for this one, because it's a 1/3 distance, plus finally the last one, which is at a distance of 1 plus a third, which is 4/3, 4 squared d squared over 3 squared. Okay, again, this one should be 2 squared over 2 squared d squared, which is 4d squared, okay? So the bottom line is we found the moment of inertia, the torque acting on the object at t equal to 0. This is a very important point in here. All the torques are positive because this one is going counterclockwise. So is this one, by the way, coming from M2, from this particle 2 and from particle 1. They are all going counterclockwise, so they are all in the same direction. So all the torques are positive. So the torque in this case is the sum of all of these three torques. And the torque in this scenario, it's easy. It's mass times the distance. That's it, because the force in this case is, okay. Yeah, in this case, the R is pointing this way, and the wait a minute, it's spinning in that direction. It doesn't mean that this torque is, sorry, take it back, take it back, take it back. This is mg pointing down. This is mg pointing down, and this is mg pointing down. So yes, you're right. Sorry about that. So this torque is actually negative, okay? Because the right-hand rule will point it so that the torque is actually in the opposite direction, okay? So the torque in here is actually trying to spin it this way, although the object is rotating in this direction. So this is against the direction of rotation, but this one is a positive, and so is this one. Both of these two are torques in the counterclockwise in the same direction of rotation, whereas this torque is against the direction of rotation. So I'm sorry. So let's recalculate these torques again. Tau, then in this case, is equal to, this one is going to be negative mg, that's the strength of the force, times the distance, which is 2d over 3, plus this one is positive, mg times the distance d over 3, plus mg for the last one times the distance, which is 4d over 3, okay? And you do the summations, you have the masses, you don't have the masses, it's all symbolic at this point. Okay, the angular acceleration at t equal to 0. So we have tau, we have I, we should be able to find alpha equals to tau over I, okay? So that's basically the linear acceleration of particle number label 3. So once you have alpha for the entire system, you should be able to find A, which is for that one, for label 3, it's a distance 2d over 3. So it's going to be alpha times 2d over 3. So again, I'm assuming that you did the calculation on here so that you can find what this acceleration for particle 3. This is not for each and every one of them. So this is the acceleration with which it's trying to go upward, okay? And the maximum kinetic energy. The maximum kinetic energy compares to this configuration. So right now, the object is, the system is in this position. When it spins around so that the center of rotation stays in here, this will have gained the potential energy, this would have lost potential energy, and this would have lost potential energy. The distance in here is 1/3 of a d, the distance in here is 4/3 of a d, and the distance in here is 2/3 of a d. So basically, there is a gain of potential energy for one of them as a gain height, but the other two lost potential energy, and that would correspond to a gain in kinetic energy for this one, a gain in kinetic energy for this one, and a loss of kinetic energy for this one. And you combine everything, and you should be able to find the maximum kinetic energy in this configuration when it's spun. But obviously, if it's going to continue spinning, it's going to lose some of that kinetic energy and so on and so forth. Okay. The maximum angular speed. So once you find the maximum kinetic energy from the conservation of energy using just the potential energy, you're going to use the fact that the kinetic energy, which is really 1/2 of I times omega squared, must be equal to the change, in this case, the maximum kinetic energy that you compute from the calculation of the potential energy. Once you do that, you can find omega max, because this should be Ke max when it's in this configuration, which is just whatever the formula is on the other side, and that the square root 2 times that change in potential energy, delta PE, okay, divided by I, okay, and then the square root because it was omega squared max. and the maximum speed for a particle. Once you find omega, you can, if you're interested for the speed of particle 2, then in this case it's going to be V max for that particle is going to be just the distance, which is 1/3 of a d times that omega max. So 1/3 of a d times that omega max. Okay, quickly here. What time? Oh man, 20 minutes already. So we still have 11. We still have 12. So I probably have to do another video, and that will be the last video, because remember, we still have not talked about 9. Okay, and that's an important one. Okay, so let's see here if we can do another 5 minutes at least for another problem. So for this one in here, it says that number 11, a mass of 0.0, basically a 5-gram bullet traveling at with a speed of v naught equals to 1,000 meters per second strikes an 18-kilogram door embedding itself at a distance 10 centimeters, or what distance in here today? 10 centimeters from the opposite side of the hinges, basically this distance when the bullet travels in. So we have V naught, we have the mass of the bullet, we have the mass of the door, we have this distance, and we have the length, the width of the door, basically, as it's open, which is 1 meter. And before it hits the door, does the bullet have angular momentum? Yes, it does, because the angular momentum, the formula for it, is equal to r cross p. So the vector r cross with p is equal to mv naught in this case. So L naught in quantity is equal to r times mv naught, where r is actually, let me draw the geometry. So this is the door. This is where the bullet is. This is where r is. So at this point, the bullet is in here, traveling toward that. And as it hits the wall, it's this vector r crossed with the momentum, which is in this case mv naught. So this is two vectors. One is pointing toward the center of the hinges, because that's going to be the center of rotation. So that's where the door is going to swing afterwards. So from where the particle is to that, so that's the vector crossed with mv naught. So if we do the math, so it's times the sine of this angle, okay, sine of theta, okay. And it's clear from the geometry, you guys can clearly see that the radius in this, the distance r in this case, is the hypotenuse in this right angle triangle, and r times sine theta is exactly this distance, which is L minus 10 centimeters or d, okay? So it's 80 centimeters. So in this case, L naught is equal to the mass times V naught times L minus d, okay? That's it. So yes, it has a momentum, and you can compute it. The mass of the bullet is known. V naught is 1,000 meters per second. L is 1 meter, and D is 20 centimeters, 0.2 meters. So this is computable. Not just it has, but we can compute it. So that's how much angular momentum there is for the entire system. Okay, and is the mechanical energy of the turntable. I'm sorry, what am I doing here? I'm sorry, I think the next problem. Okay, so if so. Evaluate this momentum. So we evaluated it. If not, explain why. So there is no answer to that question. I mean, it doesn't mean any sense. So there is, we computed it. Is the mechanical energy of the bullet door system constant during this collision? Answer without doing calculations. So in this case, the collision is going to be an elastic collision, because it's going to embed itself in it. And since it's not elastic, then it's not going to be the mechanical energy in this case, the kinetic energy is going to be different. So there is a loss of energy in this case, okay, due to heat and other things. At what angular speed does the door swing open immediately after the collision? So the conservation of angular momentum requires that first of all, the initial momentum is equal to LF, and LF is equal to I times omega final, okay? So from here, we can find the angular velocity at which it's going to be spinning. So it's the initial one divided by I. And I, in this case, is that of a door. So in this case, I'm going to assume that it is of length L. So it's going to be 1/3 of ml squared. 1/3 of ml squared times the plus the what the m is actually a combination of how much is the mass of the door? It's 18 kilograms plus a 5 grams, so it's not going to make much difference in it at all. So the point being in here is that we have I, we have L naught. We should be able to find what this value is. So remember, I in this case is going to be 1/3 of the mass of the door plus that tiny bullet, if you like, times, and the bullet is at a distance, so I have to be careful in here. So it's 1/3 of m times the entire length squared plus the mass of the bullet times the distance, which is in this case L minus d squared. Okay, that's how far it is from the center of rotation. Okay, because I'm going to assume that the bullet is a point particle. Okay, so that is basically the formula for the final omega, and then calculate the total energy of the bullet after. So we can calculate the 1/2 of I omega squared, since we have I, we have omega squared. That's going to be the remember, the door doesn't go up and down, and this is a horizontal view of the door. Okay, so there is no potential change in potential energy, must be equal to 1/2 of mv squared, mv naught squared. So the change in the and the total energy is actually equal to the change in the kinetic energy only, and the change in the kinetic energy is going to be 1/2 of I omega f squared minus 1/2 of mv squared naught. So this is the mass of the bullet, velocity of the bullet squared, and you're going to find that this number is actually negative, so there are losses in the energy. Okay, so I think we're going to stop in here. So we still have 12, okay, and also 9. Since 9 I didn't know it, it requires a little bit of thinking, but free body diagrams and so on and so forth. Okay, I'll see you for the final review, for the final video for this review. Thank you.